Hello, this is Dr. Joe Trout from the physics program at Stockton University. This is part two of chapter 7, time series regression models. We want to use the time series as predictors for some variable. So the time series data are observations collected at regular time intervals, and predictors or features are variables used to improve the forecast accuracy. And the goal is to identify variables or transformations that capture signals, trends, and seasonality. So we can look at lag features. These are past values of time series that are used as predictors. So for example, if we're predicting y at t, then we might look at values for y at t minus 1 and y at t minus 2. And this is used to capture autocorrelation, and it's essential for AR models. We can also use things like rolling window statistics. So here we have a moving average, and this will smooth fluctuations and capture local trends. There's also rolling standard and deviation and variance, and these capture changes in volatility. And these are used by feature engineering for stability or for detection of anomalies. We also can look at time-based features so we can extract from the timestamps the hour, day, week, month, quarter, or year, and day of the week or weekend or holiday information. So we can use this to capture seasonal effects and calendar-driven patterns. So for example, we can use seasonal decomposition and look at the trend or seasonality or the residual extracted using, for example, the STL or the seasonal trend decomposition, Ewing-Lewis, and the classical decomposition. So the use for this is to model components separately or use trend seasonal signals as features for your predictions. We also can use things like Fourier series terms. So these approximate seasonal effects using sines and cosine waves. So for example, if we were to take the temperature in New Jersey, we would see that it gets hot in the summer and cold in the winter, and hot in the summer and cold in the winter. And if we were to look for the monthly averages, this would approximate a sine wave. It doesn't actually come out to be a sine wave, but it's close enough we can make predictions using sine or cosine waves. And what we have is the sine of 2 pi kt over the period, where the period is capital T. So here's a good example. Here is data that's collected by the Hubble Space Telescope, and it was staring at a star and watching the luminosity of the star. So watching how bright the star was. And what we see is that the star was actually pulsing on and off. So we get brighter and dimmer and brighter and dimmer and brighter and dimmer. And it seemed to have a period. So this is 1034, and this is 1036. The times, this is called BJD time, which has to do with the fact that as we're spinning, the universe is changing. So we use something called BJD time, but a day is still 24 hours roughly. So if we look here, these are days, and this is 1034, and this is 1036. So it looks like we have a um, 2 days here, and it looks like, let's start here. It starts at a minimum, it reaches a maximum, goes back to a minimum. That's once and maybe twice, right? So we had this oscillation that's taking place uh, twice every 2 days, so it's about a 1 day. So if we look at the Fourier transform of this, what we see is that there's this peak at about 1 day. Now, there's also other things happening, and that's what these other peaks are for. But from here, we can figure out what's going on with the star. So here, the periods of oscillation aren't a year or even a day. Well, they are a day, but we can use the Fourier analysis to figure out what these actual periods are. We could also use difference series, and the first difference is just y of t minus y of t minus 1. So if we use differencing, we can use that to remove trends and make non-stationary data stationary for modeling. And we'll talk much more about that in chapter 9. We also look at the model-based features, so we can use residuals and fitted values or hidden states. And we'll talk more about this also in chapter 9, the ARIMA model, and we have some other models that we can use. So feature selection techniques, they look at correlation analysis. So we might see how your variable compares with another variable. And we could look for causality. And there's the Granger causality test for that. We can use the ridge regression. And we can also use permutation importance. These are ML models. And we'll talk more about these in a couple of chapters. And we want to identify the most predictive and non-redundant features. We also want to talk about something called dummy variables. And this is a yes or no is replaced by 0 or 1. So for example, if we look at the day of the week as a predictor, then the following dummy variables can be created. So for example, we have D1T and D2T and D3T and D4T and D5T and D6T. And if you notice, there's 6 values here. And for instance, Monday would be 1, 0, 0, 0, 0, 0, and Tuesday would be 0, 1, 0, 0, 0, 0, and Wednesday 0, 0, 1, 0, 0. And we can use these dummy variables as actual variables. And if you notice, there's only 6 of these, and there's 7 days. That's because Sunday is 0, 0, 0, 0, 0, 0. So we only need 6 dummy variables to represent 7 days. So the TSLM model will automatically handle this situation and specify the predictor season. So let's take an example. We want to forecast the value of future beer productions, and we can model this data using a regression model. So what we're going to do is have B0 and B1T and B2, D2T and B3, D3T and B4, D4T, and plus some residual. In this case, DIT is equal to 1 if T is the quarter I and 0 otherwise. So the first quarter variable has been omitted so that the coefficients associated with the other quarters are a measure of the difference between the first quarter and those quarters. So we're going to forget about the first quarter, and that's why we have just D2, T2, and D3, D3T and D4T. So if we look at the beer production, and this is the quarters, and so once again, we're using dummy variables, and uh, so in this case, we have Q1 and Q1 and Q1 in 2005, and the other quarters would follow, right? So we have Q1 and quarter two and quarter three and quarter four as we go back through the thing. And in this case, it's measuring megaliters, and it's the Australian quarterly beer production. So if we go ahead and run the TSLM model, and we're going to look for trend and season, and we'll go ahead and estimate B naught and B1 and B2 and B3 and B4. And the first value here, these are the estimated values. And the first value would be the trend, and then the betas for these different values. So we find the betas and the trend, and then we can, and the intercept. So this part is the trend, and this part is the seasonal part, and we'll go ahead and look at these values. So we'll go ahead and plot our estimate versus the actual values and or the fitted values, and the data is in black, and the fitted value is this orange or brown color. And what you notice is that it captured the seasonality pretty well, and it didn't do badly, but you could see that sometimes it missed a lot. So what we see is that there was a slight trend down through here, right? And also the seasonality that we're talking about. So if we go ahead and plot these, the fitted value versus the actual value, what we should see is that they should lie along this straight line. And if it does, then we see that it's a pretty good fit. So here's another example. And here's the data file that we loaded in. And here's the libraries that we needed. So readr and the other variables that values that are listed here, mostly tsybl and Fable tools. And what we'll go ahead and do is read in the data, and we'll call it sales data, and then we'll preview the data. And then the data was in a strange date pattern. So what we did was rename the column names to make it a little bit clearer. So it observation date and sales at millions of dollars. And then we'll go ahead and convert the observation date to a year month format. And then plot the data. And then we'll fit a model using trend and season. And then we'll make a report of the fit. And then we can forecast the next 12 months and then plot the data. So we see this is the data that they had. And what you can see is there's definitely a trend here, right? And also we see that there may be some seasonal component because it is oscillating up and down at a somewhat regular portion, it looks like. So if we go ahead and run the model, we get a value that looks like this, right? Okay. In the blue shows, the dark blue shows the 80%, and the lighter blue shows the 95%. And that blue line is our projection. So in this case, we can go ahead and find out what the trend is and the intercept, and then go find the beta values for year 2 through year 12. So here shows our actual versus our fitted sales over this time frame. And if we plot the actual sales versus the fitted sales, we can see that it does a pretty good job at predicting this. And it's hard to tell, but there's um, a solid, a dotted line here. And what you may notice is that it's a little bit above at this point, and a little bit below at this point, and a little bit above. So it's not the best prediction that we could ever make, but it's not horrible. So we also have something called intervention variables, and an intervention variable represents external events or changes that affect the time series in a specific point of time. You'll find these are also used with the ARIMA models that we'll talk about in Chapter 9. And some examples are like a new tax law might come out that'll shift your data, or a product launch or recall might really affect your data. You know, the product launched in a good way and the recall in a bad way, or the COVID-19 pandemic, right? Or marketing campaigns. These are all intervention variables that might happen once and might have an effect, and and we can pinpoint pretty much where it happened. So the purpose of these are to model and quantify the effect of these discrete events on a time series, and it'll help adjust your forecast or understanding structural changes. So the types of interventions are a pulse. This is a temporary. This is for sudden, short-lived effects, right? So like maybe a one-time sale, right? Or step, this is permanent. So these are long-term level shifts. So for example, maybe there's a new regulation or a new tax or something like that. And a ramp is a gradual. So this is a slow increase or decreasing effect over time. So a lot of times the effects of COVID-19 could show up as being something that slowly took effect, and then maybe it lowered all of the sales, if you know the sales reports for the time that the COVID restrictions were enforced, and then once they were lifted, it also took a while for things to come back, right? So maybe you want to use a ramp or a gradual, slowly increasing or decreasing effect over time. So in time series modeling, what we would have is that our predicted variable will be whatever our model is, maybe an ARIMA model that we'll talk about in a little bit, and plus uh, this intervention variable, right? And for a pulse function, what we would see is that IT would equal 1, then T was equal to T0. And it would equal to 0 if they were not equal. So if it wasn't the day of the sale, then it would be 0. If it was the day of the sale, it would be 1. We also have these step functions, right? So once again, if T is less than this day that the tax took place, then IT would be 0. And if it was greater than the date, then IT would be 1. And by IT, we're talking about the intervention variable. And IT would be, for a ramp function, IT would be 0. And then it might be the time minus T1 plus 1. So it would slowly ramp up after the day. So in analysis, we identifying the time and the nature of the intervention, and then create an appropriate intervention variable, and then estimate the effect using regression with some other model. So we also have things called training days. Trading days. So for example, the number of trading days in a month can vary considerably. So if you were just to take like your total sales per month, well, there's different days in the month. Or if the only time you were making money was during trading days, then it could get a little messy if there was a bunch of days that it was closed. So maybe um, in July, for example, during July 4th, right? Maybe it'll be closed for 1 or 2 days or something like that. Or during Christmas, it'll be closed, or New Year's Day. So, and also there's different number of days in the month. So if we're looking for the number of trading days in a month, these can vary considerably and have a substantial effect on sales data. So to allow for this, we'll take the number of trading days in each month can be indicated as a predictor. So an alternative is that allows the effect of different days of the week as the following predictor. So X1 would be the number of Mondays in the month, and X2 would be the number of Tuesdays, up to X7, which would be the number of Sundays in the month. We can also model with distributed lag. So this is often useful to include advertising expenditures as predictors. So don't forget, we're going to put a bunch of predictors together and we're going to use the ones that are, we use just enough predictors to make a good model, but we don't want to um, over predict or have too many predictors. So what we need to do is include these, we can include lag values of advertising expenditures, and thus the following predictors could be used. So X1 could be advertising for previous months, and X2 advertising for 2 months previous, and XM advertising for M months previous. So it's common to require the coefficients to decrease as the lag increases. So how do we select these predictors? So how do we do it? Well, we can plot the forecast variable against a particular predictor and see if there's no noticeable relationship, then drop that predictor from the model. Or we do a multiple linear regression on all the predictors and disregard all variables whose p-values are greater than 0.05. So in essence, we look at each predictor and see if it is going to be useful in predicting the future. So here shows some of the stat tables that can be used, right? And in this case, we're going to load these libraries, Broom, Mumin, and Boot, and we'll download a linear temperature example. So this was some dummy data that we had made up, and then we'll fit the linear model. So in this case, we're going to use LM, and we'll use our T will be the time, and the data will be the data that we read in from our file, and then extract the detailed model data. And we can use something called glance, and then we can compute the cross-validated variables and take a look at them and see if these predictors are important or not. So we really have 5 methods, or there's more than 5 methods, but 5 that we'll look at here. There's the adjusted R squared, there's cross-validation, there's AIC, and then the corrected AIC, and then Schwarz's Bayesian information criterion. So all of these will help us select our predictors. So first, using R squared, or minimizing the sum of the squares, and we already talked about this, right? If R squared is equal to 1, then the data all lies on our model, right? And the R squared values are a good method for measuring how well a model fits the historical data, right? So if all the historical data lies on the model, then R squared will be equal to 1. But it's not a good measure of the predictive ability of the model to forecast future data. So R squared will tell you really well if your model fits the data, but not if your model will predict the future data. So we use an adjusted R squared value. So they can use, a lot of times it's written as R squared bar. And this is a version of R2, R squared, excuse me, that penalizes for the addition of irrelevant predictors. So for example, let's say you believe that your weekly pay will depend on the hours you work and um, how well tips went that week, and I don't know, the sales that are going on in the restaurant, and a few other things. Well, they might be important and they might not. So you'll build your model looking at all these predictors, and but if you the more predictors you put in, the better the model is going to fit. But it doesn't mean that these predictors are actually helping out, right? It doesn't mean that they will help you predict the future. So unlike R squared, it decreases when a predictor doesn't improve the model. So if we look at N or T equal to the number of observations and P or K equal to the number of predictors, then we end up with our R squared value is 1 minus R squared. So this is how well your model actually fits the data. And then the number of observations minus 1, and then the number of observations minus the number of predictors minus 1. So you'll either see it written in terms of N and P or T and K, where T is the number of predictions and K is the number of predictors. But once again, these are two identical equations. Just in this one, they're using N and P for the variables, and here they're using T and K, and this is what your book is using. So we have the R squared value. It equals 1 if all the model, if all the points, observed points, fit on your model. And now we have the adjusted R squared, which takes into account the number of observations and the number of predictors. So here's a good example. If we look at the interpreting the R squared values, the adjusted R squared values, higher is better, but the context matters. And if the adjusted R squared increases after adding a predictor, it's likely more useful. If it decreases, the predictor may be just creating noise in your model. So for example, here's two models to predict the same variable, like future sales. Here they use two predictors. Maybe it was advertising costs and things like that, and people's average income. And here they use 5 predictors. So maybe there was 3 more things that they included in the model. So if we look at R squared, it of course got better when we added more predictors. That'll always happen, but not by much. But the R squared value actually decreased. So it looks like model A is preferable because model B added complexity, but it really didn't help you at all. So always report the adjusted R squared along with R squared in model summaries. We also have cross-validation. So cross-validation is resampling method to evaluate how well the model generalizes to an unseen data. So why is it used? It detects overfitting. So for example, if you keep adding in variables, right, then your model is going to fit the historical data better, but it doesn't mean that you're going to be able to predict the future better. And it's also going to help choose between models or predictor sets. So the type of cross-validation, there's k-fold cross-validation, where the data is split into k parts, and you train on k minus 1 parts, and you test on 1, and then you repeat. Or leave one out, which is a special case of the k-fold, where your k is going to be equal to n, the number of observations. And what you do is you leave one out, and then you use your model to predict that one. So you use all the other variables as training information, and then you use it to predict the one that's missing. And there's also repeated CV, or cross-validation. And this is a k-fold repeated multiple times to check for stability. So k-fold validation, what is it? It's a model validation techniques that splits the data into k equal parts or folds. And then you train the model on all of the parts except for one. And then you create your model, and then you test the model on the remaining one that you didn't include. And then you repeat it k times, each time with a different test fold. So for example, how it works. Let's say k equals 5. We split the data into 5 equal parts. We train on 4 parts and test on 1. And then we rotate the test fold, and we average the performance over the 5 tests. So why is it used? It reduces variance from single train test splits, and it gives a better estimation of the model's generalization. So don't forget, you can make a model fit your historical data perfectly, but that doesn't mean it's going to predict what's happening in the future, and that's what we really want. So it works well for small to moderate data sets. So common choices are k equal 5 or 10, and there's a stratified k-fold for classification with imbalanced classes. And we average over the root mean square or r squared over the folds. So we also have leave one out cross validation. So in this case, it's a special case of the k-fold where k is actually equal to n, the number of observations. So for each observation, we train the model on all the data except for that one data point. And then we test the model to see if it can predict that left out observation. And then we repeat it for all n observations. Then we compute the average test over across all n trials. So one thing is that there's n iterations, so it possibly could take a little while, and each data point gets a turn as being the test case. So the advantages, it uses almost all data for training in each iteration. And then it provides an unbiased estimate of the generalization of the error. And it's useful, especially when data is limited. The disadvantage is that it's computationally expensive for large data sets. So the bigger n is, the more models you have to do. There's also a high variance, so each training set is very similar, so estimates can be noisy. And we can also lead to over-optimistic performance on noisy data. So the bottom line is that this leave one um, variable out is a powerful for small data sets, but the k-fold CV is often more practical and stable. So for regression models, it's possible to use the classical leave one out cross-validation to select predictors. So the procedure uses the following steps. So remove the observation from the test set and fit the model using the remaining data, and then compute the error. So you do YT minus your so the actual data minus your predicted data for the emitted observation. And this is not the same as the residual left, right? When the teeth observation was not used in estimating the value of the predicted value for Y. So don't forget, you didn't use this point in the model. So then you repeat it for t equals 1 through t, the number of observations you have, and you can compute the mean square error of E1 up to ET and call this CV. And it looks time-consuming procedure, but use fast methods of calculating CV. And the equation for computing CV is efficiently and is given in section 7.9. We also have AIC, and AIC is a measure of the of model quality that balances goodness of fit with model complexity. So the formula is that AIC is equal to 2K, where K is the number of model parameters, minus 2 times the natural log of L. And L is the maximum likelihood of the model. So it minimizes, the goal is to minimize AIC, and lower AIC indicates better models. And of course, the software is going to take care of this for you. So the key features is it penalizes models with more predictors to avoid overfitting, and it encourages simpler models that still fit the data well. So using AIC for predictor selection, it lets you compare multiple models, and it differences, if the AIC differences are greater than 2, then generally considered meaningful. So how to use it? We fit the several candidate models, and then we compute AIC for each model. So for instance, model 1 may have 3 predictors, and model 1 might have 2 predictors, and model 3 might have, let me try that again. Model 1 may have 2 predictors, and model 2 might have 3 predictors, and model 3 might have 1 predictor. But when we compute the AIC, we see that model 3 has the lowest AIC. So that's probably the model that's going to do best. These increase, like using X2 and X3, 2 more predictors, would probably model the historical data better, but it doesn't mean that it's going to be the best model to use. So if we look at AIC, this is a closely related method in which we define AIC to be log time t times the log of the sum of the square errors over t plus 2k plus 2, 2 times k plus 2, where k is the number of predictors. So the corrected AIC, for small values of t, the AIC tends to select too many predictors. So a bias correction version has been developed, in which case we take the AIC plus 2 times the number of predictors plus 2 times the number of predictors plus 3, and then the number of samples minus the number of predictors minus 3. And once again, we're trying to minimize this number. We also have the Schwartz-Bayesian information criterion, and this is also a measure of how well your model is doing, and compares and uses the number of predictors. The more predictors, then the more complex it is, and this will be a measure of it. So as with AIC, we're trying to minimize this BIC, which is intended to give the best model. So the model chosen by BIC is either the same as those chosen by AIC or one with fewer terms, right? So BIC penalizes a number of parameters, the number of parameters more heavily than AIC. So the Bayesian information criterion, BIC, is a criterion for model selection based on the likelihood function and a stronger penalty for AIC. It has a stronger penalty for complexity than AIC. So BIC equals K, the number of predictors, times ln, the number of observations, minus 2 times L, and then L is the maximum likelihood of the model. So lower BIC means a better model, and it penalizes complexity more than AIC. So it prefers simpler models, especially for larger data sets. So if we're using BIC for model selection, when to use it, when overfitting could be a concern, and for larger sample sizes, there's a penalty increases with the log of the natural log of n. So you want less complex models, and this will be a measure of it. So if we look at the criterion AIC and BIC, if it penalizes complexity, so BIC measures it higher than, penalizes more than AIC, and more conservative BICs. So if we look at a model and we look at the predictors and we list out the BIC, which will be computed for you in many libraries, then we pick the one with the lowest BIC. So if we look at parsimonious models, it's a model that explains the data using the fewest predictors necessary without sacrificing accuracy. So the key characteristics are simple. There's a few variables and less complexity. It's efficient, it avoids overfitting, and it's interpretable, so it's easier to understand and communicate. Why it matters, it reduces noise and multi-collinearity, and it also improves generalization to new data. And it follows the principle that Einstein paraphrased. Well, this is a paraphrase of something Einstein said: as simple as possible, but no simpler. So how to achieve it? We use model selection tools like R-squared, AIC, BIC, and cross-validation. And we remove redundant or insignificant predictors. And the bottom line, choose the simplest model that performs well enough, and it's not necessary to make it the most complex one. Complexity will always increase your R-squared value, and it will always get closer to 1 the more predictors you input in, but that doesn't necessarily mean that it will be effective or efficient. So for example, Here's a 16 possible models for forecasting US consumption with 4 predictors. So the predictors are income, production, savings, and unemployment. And if you notice, if we look at the adjusted R squared value, right, we want the highest number, right? So with the adjusted R squared value, we see that if we include all of these predictors, we get the highest R squared value, right? If we start to take out predictors, and for instance, in the second model, we don't use the unemployment data, we still get a pretty high predictor. And if we don't use the production, we still get a pretty high predictor, right? If we use just the income and the unemployment, then our model doesn't do so good against according to the adjusted R squared value. If we look at cross validation, right, then if we look, right, we see that if we use all 4, it comes out to be about 0.104. If we use 3 of them, not including the unemployment, it comes out to be 0.105. It's about the same. And if we take out production instead, we're still really close. Okay. If we look at AIC and the corrected AIC, right, we notice that the more predictors we have, the higher these values are, right? And so once again, we're trying to find the best model using the fewest amount of predictors. And we'll look at all these values and see which ones we think is acceptable. So when we forecast with regression, what we're going to look at is YT equals some constant, beta naught or beta 0. And these are our predictors. And these are the values we're going to fit the predictors with, right? So which comprises the estimate coefficients, and ignores the error in the regression equation. And plugging in the values of the predictor variables returns our fitted value for Y. And instead of in forecasting, instead interest and it's for interesting in forecasting future values for Y. So if we're looking at our forecasting types, the forecasting is the process of making predictions based on past and current data. There's 2 key types. There's ex ante and forecast, which is before the event, and ex post, which is after the event. And the purpose of this distinction is to understand whether the predictions were made with or without the knowledge of the actual outcomes. So for example, if we're testing our model, we'll train it on part of the observations and then predict the remaining data. And we want to evaluate model performance honestly and fairly. So if we look at before the fact, right, these are made before the outcome is observed, and it relies on historical and current data, and it mimics real world decision making. So some examples are predicting next month's sales using current market trends, economic policy planning based on past performance, and use for real-time forecasting and planning. With ex post, after the fact, these are made after the outcomes are known, and it uses the entire data set, including future values, and it's often used for model evaluation and retrospective analysis. So for example, you make a model, then you wait a couple of days and you predict the future, and then the future happens and you do the same test over again and see how your model really did and what you could have done to improve your model. So these are good for refitting a model using full data, including the target period and back testing a model on historical data with known outcomes, right? So that's, if you make a model, you should use some test. You should take your date, your time series, and make part of it the test data and part of it, or the model training data, and part of it your prediction data, and predict what you already know and see if how well your model does. And this is used for analysis and model validation and not for decision making. So if we consider ex ante and ex post, right? Timing before the outcome is known, after the outcome is known. Data use for is past and current data only. And here we have the entire data set. This is used for real world decisions. This is used for model evaluation and backtesting. This is low risk of, if done properly, for bias risk, and high risk for future leakage risk, right? So if we are so convinced that we've modeled the historical data exactly, then we might be tricked into thinking our model will predict the future very well. And the goal here is to predict the future, and here is to access model accuracy. So for example, let's go ahead and look at forecasting with regression. So what we have are megaliters of beer versus quarter. And we're going to look through the beer production, and we're going to start with quarters. We're going to use quarters that are greater than 1992. Then we'll fit the beer data, right? So we're going to model using TSLM. We're going to use the trend and the season. And we're going to forecast. So we're going to fit the beer, and then we're going to forecast what happens. And let's auto plot our recent production. And we have forecast of beer production using regression in megaliters. So here's our training data to train the model. And here's what we use to predict using the model. Once again, if you can see, there's a thin blue line that runs through here. And then our 80% level and our 90% level are showed in these two colors. So here's another example. I'm sorry. So this is US consumption, and we're using percent change. So we're going to look at future scenarios. And with the increased, well, the new data of the US, and we're going to mutate the income and sales and unemployment by 1 and 0.5 and 0, and then we'll decrease the new data and then mutate it by -1, -0.5, and 0, and we'll name it scenario IO. And then we're going to forecast, fit the best data, right? The new data and the future scenarios. So we can look at the US change, and we'll auto plot consumption and our auto layer and put the labels on, right? So in this case, we're going to look at two different models. One where we have a decrease, and one that we have an increase using these two sets of values. And then we can go ahead and set up our 80 and 90% values and look at what our predictions are. So when we were building a predictive regression model, right, we can have an alternate formulation that uses predictors as to use as predictors their lag values, assuming we're interested in generating H step ahead forecast, right? So we have Y T plus H, and we have a constant, and then our first predictor is X1, and our second predictor up to XK, and we have our error term. And for H equals 1, 2, up to whatever. And the predictor set is formed by the values of X chosen that are observed H time periods prior to observing Y. So therefore, the estimated model is projected into the future beyond the end of the sample T, and all the predictors are available. Values are available. So for example, if we're building a regression model, we may have um, just a constant and then beta 1 times 1 predictor. And for our 95% and our 80%, right, we'll use 1.96 and then sigma E, which is the standard error regression, and SX, which is the standard deviation of the observed values. So this is the formula for how we're coming up with this 95% and this 80%. And I'm sorry, this should say table 7.1, not 5.1. So we can install some packages to do this work. So one of them is called Broom and the other one's called Matrix. And I've set up a fictitious time series data, and you can read in the file and convert the dates in the date column so they'll be usable. Because don't forget, a lot of times these dates are coming in as a day and a month as a 3-letter indication or something, and then a year. And then we split the data into training and test sets. So in this case, there's 100 points. I'm going to use the first 90 as my test set, and the second 10, I'm sorry, I'm going to use the first 90 as my training set, and then the last 10 is my test set. So here we have an actual versus predicted, right? So if we look at the actual data is in blue and the predicted data is in orange, right? And we have our 85 percentile prediction interval and our 90% prediction interval. And we can go ahead and print out the adjusted R squared value and the AIC and the corrected AIC and the BIC and the cross validation and the root mean square error of that variable. And we can also look, so in this case, there were 3 predictors. And if we use predictor 1 alone and predictor 2 alone and predictor 3 alone, then R squared is pretty bad for all 3 of them. AIC is pretty close for all 3 of them. And AIC corrected is pretty close for all 3 of them. Because once again, they're only using 1 predictor. Then BIC and the cross validation, if you notice that the values are increasing when we go through these predictors. If we use just 1 and 2, we see that the R squared value does better. And if we use 2 and 3, the R squared value does better. And if we use 1 and 3, it does not as well as the other 2 combinations, but it does better than just any of the single predictors. And if we use all the predictors, then of course the R squared value is fantastic, right? Or at least the best that it's been for any of them. However, if we look for AIC and the corrected AIC, they're about the same. And BIC is about 560, right? And our CRMS comes out to be about 4.9. Right? So from this value, we can see which predictors were actually beneficial with making this happen. So we can actually look at the prediction. So this is using just predictor 1, and this is using just predictor 2, and this is using just predictor 3, right? So using just predictor 1 didn't actually, it probably did the best of them all. Then if we look at 1 and 2 and 2 and 3 and 1 and 3, so once again, we're just using those predictors to make the model. It looks like 1 and 2 did pretty well, and 1 and 3 did pretty well. And I think this isn't surprising since 1 did pretty well by itself, right? So the fact that 1 and 2 and 1 and 3 did pretty good may just be that predictor 1 was really, really important. And once again, as we look through here, you can see that, for instance, if we look at 2 and 3, like 1 and 2 did pretty well, 2 and 3 did pretty well, 1 and 3 did pretty well, and all the predictors, of course, fit the data pretty well, right? So don't forget, we used the first 90 points as the training set and the last 10 points as our model test set. Also, sometimes things are non-linear. So instead of having a linear trend, so for instance, the current through an RC circuit drops off and it's definitely not linear. However, I know that like if I do all the math, I know that the current is equal to the initial current times e to the minus t over tau, where tau is some constant. And this is the lower Greek letter tau. However, if I take the log of both sides and I take the log of the error versus time, it comes out to be a straight line. And using this value, I can figure out what tau is. Right? So this is the data I collected. And it's non-linear. However, if I take the log of this, it suddenly becomes linear. So this can really help you out. If you take your data and you see a curve like this, you might try taking the log of it or the natural log of it, or taking a natural log of both variables. So what we're doing mathematically is we're dividing both sides by the initial current. That's what I naught is. And taking the natural log of both sides. This gives us, I don't know if you know this, if you remember this from math, but the natural log of A over B equals the natural log of A minus the natural log of B. So then we can set this up and we note that this becomes a straight line. And what we see is that our y-intercept is just going to be the log of I naught. And our slope is equal to minus 1 over tau. So if we calculate the slope, we can figure out what tau is. Once again, most of this will be done for you by libraries and packages. However, you should understand what they're doing. So if we have something nonlinear, if we take the log of either one variable or both variables, we can figure out what beta naught and beta 1 are and use, for instance, the slope of this line to find B1, and the y-intercept will be B naught. So these were times run during the Boston Marathon. And this is an example from your book, and the data comes from the FPP2, or excuse me, FPP3 library that's stored in there. And what we can do is use the linear TSLM model and look at the trend and the trend. Now, note that there actually seems to be 3 portions here. So if you look at this data closely, what you'll notice is that it was like starting to drop, and then it started to drop faster, And then it kind of started to become constant. And the model we're going to use are exponential and linear and piecewise linear. And we've plotted all three of them here. And what we see is that the piecewise one did the best. So we have the linear. This just uses the trend. The exponential will use the log of the minutes and the trend. And then the piecewise uses the minutes and the trends. And the dots are at 1950, where this starts, and 1980. So it fits a line to this portion, and then it fits a line to this portion, and then it fits a line to this portion. So we also want to look at correlation, causation, and forecasting. And forecasting with correlated predictors, the challenge is that when the predictors are correlated with each other, that's called multicollinearity, then forecasting accuracy and model stability can actually suffer. So why it's a problem is that the coefficients become unstable and hard to interpret. These are the coefficients, the betas we're trying to figure out. And small data changes can have large swings in predictions. And it's hard to tell which predictor is really important. So for detection tools, we have something called the correlation matrix and the variation infiltration factor, the VIF. And if VIF is greater than 5 or 10, it may indicate serious multi-collinearity, where the predictors, the variables that you're using for predictors, are actually collinear, right? And they depend on one another. So we remove or combine the redundant predictors and use something called principal component regression, PCR. And we can also apply something called ridge regression, which shrinks the correlated coefficients, and choose simpler models with fewer predictors. So forecasting works best when the predictors are informative but not redundant, and always check for collinearity before testing your model, trusting your model. So correlation is not causation. So just because two variables move together doesn't mean that one causes the other. So for example, ice cream sales and drowning deaths both rise in the summer. Are they causality linked? Probably not, right? They're both influenced by a third variable, temperature. So there's a common pitfall is misinterpreting correlation as evidence for cause-effect relationship. And this happens a lot in science, right? But that's why we have peer-reviewed journals for people to look at the data and make sure that this isn't going on. So why it matters in regression is regression can model associations and not prove causality. So causal inference requires controlled experiments or strong study design. Okay, so also note that, for instance, if you take any data and you put it into Excel and you say, fit a line to this, it will, right? So it definitely will. Does that mean that there's a linear relationship? No, right? So that's kind of in the same vein as this correlation and causation I'm talking about. So multicollinear and forecasting. So if some things are multicollinear, then this occurs when two or more predictions in a regressive models are highly correlated with one another. Okay. And why it matters for forecasting, it inflates the variance of coefficient estimates and it makes models sensitive to small data changes. And it reduces the reliability of the predictor importance. a good example is that humidity and temperature in when we're predicting the weather. The higher the temperature, the more moisture the atmosphere can hold, right? So we usually use relative humidity, which is a measure of how much moisture is in the atmosphere versus how much um, how much the atmosphere could actually hold. So, for example, if there is 100% humidity, then the atmosphere has as much moisture as it can hold. However, 100% humidity in the summer is different than 100% relative humidity in the winter. So in the summer, 100% relative humidity, and there is lots of moisture in the air in New Jersey. But in the winter, 100% relative humidity, the there's much less moisture than there is when they're in the summer when there's 100% relative humidity. And if we were to look at the temperature versus and the humidity, there'll be a correlation there, right? We have to measure both, but you can see that we can't, they're not totally independent of one another. So they are correlated, at least in some way. So some warning signs are if you have a very high R squared, but insignificant predictor p-values, if we have large standard errors on the coefficients, and if we have high variation in filtration factors, right? And how to remove it, how to address it, we can remove or combine correlated variables. So for example, in the atmosphere, we actually take temperature and humidity and make something called virtual temperature. We also use ridge regression and we prefer models that are prioritized predictability, predictive accuracy over interpretability. So what we want are models with that are simple and that predict the data well. We're not going to talk about this too much, but there's actually a matrix formulation of this. So we can write this in a matrix form where we have y is going to be our observations, and epsilons are going to be our error, and beta are going to be the coefficients. And we can write this as a matrix y is equal to x, which is this matrix here, times beta, which is this matrix here, times epsilon, which is this matrix, or these are sometimes called vectors. So in this case, our epsilon has a mean of 0 and a variance of sigma squared times the identity matrix. So the goal is just to represent this as a set of matrix, and we can do that. And then when we estimate the coefficients, all we really have to do is take the transpose of x times x and invert it, and then multiply it by the transpose of x. And the requirements of that x transpose x, they must be invertible, and it fails if there's perfect multi-collinearity, right? So if you are interested in this matrix form, I will gladly talk to you about it, but you won't really need it. You won't need to know all of it for the test. But if you've had a lot of math and physics, it's actually a much cleaner version. And we have the math, we have the packages that can do this matrix algebra really fast. Right? So the advantages of matrix form are they compact and they're computationally efficient. So like I said, we have packages that can do these matrix algebra really quickly, and it enables linear-based algebra diagnostics, and we can use it to figure out what these values are. And we can talk more about this later. All right, well, thank you. And this completes chapter 7. So make sure you do the online homework and the computational uh, problem or the programming problem for this chapter. All right, thanks a lot. Have a nice day.